My name is Wade GeFellers, and I'm going to be talking today a little bit about my project is an evaluation of the plant community response following tall fescue eradication in the Mid-South. So following any kind of disturbance on the land, including eradication of tall fescue, what we are doing is promoting an early successional plant community, and these plant communities are rich in plant and wildlife diversity, but the key thing is that they are actually in decline across many areas of the United States. As I'm referring to early successional plant communities, the thing to keep in mind is that when I'm talking about these, I'm referring to pretty much what you see here in this picture. It's dominated by grasses and forbs, and these are hopefully native plant communities is what we're wanting to promote, but as you will see, that's not always the case. So several reasons that these plant communities are in decline actually exist, and they're wide-ranging, as you can imagine, from urban development to various other reasons, but the main one that I'm kind of focused on, and really the huge contributor, is the fact that many of these open areas that could be in native early succession plant communities actually are or have been converted to non-native grasses for livestock production and for hay production for those livestock as well, so grazing and or hay production. And this field you see in this picture is one of my study sites, and this is what open fields in East Tennessee look like anyways, and much of the Mid-South region, and this is just a tall fescue dominated field, and as you can see in the inset, that's just a close-up of what tall fescue looks like. So it is a non-native cool season perennial grass, and it has several characteristics about it that has made it very popular among farmers and other people as well, and for putting on your lawn, and for also grassing waterways to prevent erosion. So there are several factors, including it tolerates close grazing, unlike many of our native warm season grasses, and it can withstand multiple cuttings for hay annually as well, which is another factor that makes it very popular among farmers. And it does provide sufficient quantity and quality of forage for most livestock. And because of this, it has been called the most important pasture grass in the United States, and it now covers more than 37 million acres. And this map gives you an idea of the distribution of tall fescue. So the grayed out areas with really close vertical lines, or diagonal lines rather, shows you areas where tall fescue can grow. It's adapted to grow there. But the green area, which is centralized over essentially Tennessee and then all the surrounding states, that's the area of major use of tall fescue. As you can see, it's a huge amount of the nation that tall fescue can grow in and does grow in. Now the reason I'm concerned about tall fescue is because of its effects on wildlife, and tall fescue is virtually in every open area in the Mid-South. Even the areas you may drive by that look growed up with blackberries and trees growing in them, and you may think it looks like good habitat for quail or deer or what have you. Most of the time, in fact I would probably wager to say 95% of the time or better, there is a carpet of tall fescue under that, so it really negates any benefit those areas give to wildlife. And it has numerous negative effects on wildlife, but just to kind of skim the surface, its growth habit, it's really low. It doesn't provide structure that many wildlife species need. And additionally, the leaves, as the plant dies, they just lay on the surface of the ground, creating a very thick layer of dead vegetation, which we call thatch, and this restricts movement of species such as northern bobwhite quail, especially the chicks, turkey poults, and many species of small mammals and small birds as well. So, and additionally, it also suppresses the seed bank. Because of that thick thatch layer, sunlight cannot hit the surface of the ground, and it keeps those seeds of the native plants from sprouting and growing. It suppresses that seed bank, and it also is very invasive in that it spreads. It's a sod forming grass, and so essentially it's bad news for wildlife. But to keep in mind, all of the positive traits that has drawn many farmers and many people to plant tall fescue and the negative effects that it has on wildlife all come mostly from a symbiotic relationship with an endophytic fungus. So it is it's really interesting how the relationship works between the plant and the fungus. But this is a specific cultivar. It's called Kentucky 31. And so that's the species. When I'm referring to tall fescue, that's mainly what I'm referring to. There are non-endophyte infected tall fescue species. There is a novel endophyte, but that's much more in depth than what I'm going to go here. But just realize most of the tall fescue that we have is going to be Kentucky 31 variety, which has this endophytic fungus. Restoration of these early successional plant communities has become kind of a big push over the last several years to a couple of decades for various reasons. But the thing that I want to focus on is the fact that these restoration programs are often funded by government money. So NRCS programs such as EQIP, WHIP, CRP, and then state wildlife programs such as Working Lands for Wildlife here in Tennessee. The normal way of establishing these early successional plant communities has been to go in and plant a seed mixture. And this comes at a significant cost because these seed are very expensive. Site preparation can become very expensive. Requires special tools and equipment and then manpower as well. So these programs are funded by taxes and license sales from hunting license. So it's a significant cost to many people involved. And additionally, these plantings are often not very successful. And some of these reasons include the seed bed is not properly prepared, the planting is done incorrectly, invasive species often invade these plantings as well and causing weed competition. They're slow to establish. Oftentimes many of these grasses especially are deep-rooted species, so they spend the first couple of years sending down a root system to actually grow later. So it does take a long time for several of these species to establish. And then also patience is needed as well. So and that's one of the huge factors is many people, especially in today's world, we want results immediately, and when we have to wait 2 to 3 years to see results, it's not very favorable in the public's eye. These plantings were historically of only one or very few species and heavily skewed with native warm season grasses because early on the plantings were more along the lines of forage production, seeding rates, but we know now that that's not what we need for wildlife. But historically or early on in these plantings, the plant community that resulted actually was really no more beneficial to most species of wildlife than was the tall fescue field that was there prior to the planting of the native grasses. And one of the huge factors is there are no herbicides that are available to use in these plantings that will kill those undesirable weedy or non-native invasive species that come into the plantings, because any herbicide that is out there will kill either the grasses or the forbs that we planted. So we obviously don't want to kill those expensive plants that we just spent all that time and money planting. It has been suggested though that a high quality native plant community can be established without planting, but has never really been quantified and compared on a very large scale. I'm hoping with this project that we can develop some new management options that will help save time and money and also provide success in a short time frame, and be able to use those herbicides, which are very beneficial tools that if used correctly can promote the plant community that we're looking for. So overall, my project can be summed up in this real short sentence. We're comparing killing what we don't want with herbicides versus planting what we do want with these seed mixtures. So I have 15 study sites located across the state of Tennessee and North Alabama, and this map gives you a brief overview of where those are at. And so the project really began in 2015. We had these study sites sprayed to remove the tall fescue in November and December. Through other research, we know that that's the best time to spray to get the best results for killing tall fescue. And so as you can see in this picture, this is one of my study sites after it was sprayed, and the back portion, which is still green, is the control unit at that site where we are leaving the tall fescue. Following those herbicide treatments to kill and remove the tall fescue, the following spring we went in one of the treatment units and planted a seed mixture, as is done on these cost share programs such as EQIP and CRP and those I mentioned earlier. And so we're mimicking what would normally take place on these lands that are enrolled in those cost share programs. So this is how my study sites are actually set up. I have 3 treatment units at each study site, and we're using a randomized block design. So these treatment units are randomly assigned to either planted, control, or natural revegetation. And I'm going to take just a moment here to explain each of these treatment units. The planted units, we removed the tall fescue by spraying it, and then we came in the following spring and planted the seed mixture. And then in the control unit, as I mentioned earlier, we did nothing. We left the tall fescue, but these units will be maintained by a single mowing each year, just to mimic the traditional management on most private lands. And then the natural revegetation unit, we also removed the tall fescue from those units. At the same time, we removed it from the planted unit, so they were all sprayed at the same time. But we did nothing else that initial first year, but just let the seed bank respond. So we looked and documented what species came in just by removing the tall fescue. Data collection involves 5 systematically placed 50-meter transects in each of these treatment units. And along each of these transects, we collected data every 2 meters, and so that allows for 25 points per transect. So we have 375 total points at each study site that we collect data from. So in the natural revegetation units, we are using herbicides alone to help steer the plant community towards a high quality early successional plant community. And we're using both spot treatments and broadcast applications based on the species that have came in, and also what we're looking for and what we think that particular location is capable of producing. And most of the common species that we will be treating or have treated up to this point are Sericea lespedeza, Bermuda grass, Johnson grass, and narrowleaf plantain. And these are non-native invasive species. Now, I have knotroot foxtail on there. It's actually a native species, and I have treated it but very minimally at a few sites just because it was widely spread and I wanted to allow other plants to develop on those sites. The planted units will also use herbicides, but it'll be very strict, if you will. We are using these only according to biologist recommendations. So biologists who work with these programs, these federal cost share programs, frequently they have certain recommendations that they give to landowners who have enrolled their lands in these programs, because to remain in line with the contract regulations and be able to maintain their funding source, they have to use these biologist recommendations. So we're doing the same to try to mimic those actions so that we can make legitimate comparisons. I have several objectives with my project, but here's a few of them, and we're essentially comparing the plant community response on these different treatment units to look at species composition and then percent coverage of these various vegetation classes, structure, and then also forage and nutrition availability for white-tailed deer. And then I'll compare those to the habitat requirements for various species of wildlife that you see listed there on the screen. But for this webinar, I'm just trying to keep things kind of straightforward and simple, and so what I'm doing is comparing the percent cover of native and non-native grasses, and then also comparing native and non-native forbs between these treatment units. So as I mentioned earlier, it's a randomized block design. I'll be blocking on site to remove some of that variability that comes from site to site. And as you can imagine, with 15 study sites widely dispersed across 2 states, there's quite a bit of variability in each of the study sites. So blocking is very necessary to get results that we can use and draw conclusions on. So as I mentioned earlier, there's 25 points per transect, and I'm going to go through a few examples here just to give you an idea of how I derived numbers that we used in the analysis. So for example, transect 1, let's just say we had 14 points, so 14 of those 25 points we recorded a native grass. So basic math, 14 divided by 25 gives us 56% coverage of native grasses on that transect. Then we take the average of all 5 transects in each treatment unit to derive a single value 4% cover of each cover class. So an example of that, let's just say at the control unit at study site 1, here are the 5 percentages of native grasses. And so we do an average of those, and it gives us 23.4% native grasses in the control at study site 1. So that gives us a single value for native grasses at that unit, at that site. And we do that for each cover class. So we do that for native grasses, non-native grasses, native forbs, and then non-native forbs. And then we can subtract the percent cover of the non-native from the native, both forbs and grasses, and this gives us a single value for each treatment unit to compare across sites. So once again, let's use control, or the control treatment unit at study site 1, and we had 23.4% native grasses. If we subtract, say for example, we had 77.8% non-native grasses, that gives us a value of negative 54.4% native grasses. And so the negative value tells us that we had more non-native grasses than native grasses. And also because at each point along that transect there may be both native and non-native grasses as well as the forbs, my percentages will not add up to 100%. They may be more than 100%, they may be less than 100%. But this method gives us a single value that we can compare across study sites. So my hypotheses, essentially what I feel like will happen in the end is going to be that in the control units we will have fewer native forbs and grasses compared to both the planted and the natural revegetation units. But I do not feel like there will be much of a difference between those percentages between planted and natural revegetation units. I ended up using the Friedman's test on my data, and this is a non-parametric method to compare my data across the treatment units and across the study sites. And I downloaded Gary Ohlert's CF-CDAE package, and this gives us the ability to use this Friedman's test, and it does tell us which treatments are significantly different from others, but it does not give p-values for each individual comparison between the treatment units. So I did a little looking around, and I found a code that someone had written that actually gives the p-values for the comparisons between each of these treatment units. So let's look at the results. And so just to give a comparison, I went ahead and ran the parametric and non-parametric versions of these tests just to see how they compared between the two versions. And so I run a basic ANOVA on the parametric version, and it gave me, as you can see, a very significant p-value. So then I automatically, just from what we done in class and just from what I had, a little bit of R I have learned up to this point, I automatically thought, okay, I'll run pairwise t-tests. But at the time I didn't really think about it, but pairwise t-tests do not actually consider the blocking factor. And so with that significant of a p-value, when I run a pairwise t-test, as you can see, there were no significant differences between any of the treatment units. But then I thought about it, and then I figured out what was going on, and I run the Tukey's HSD test, and as you can see, very significant p-values between the control and both the planted and natural revegetation units. But like I assumed, there was really no difference between the planted and the natural revegetation units. They're very similar in the percent coverage of native grasses. And then looking at the non-parametric version, you can see that the package, Dr. Ohlert's package that I downloaded, there's a pairwise comparison that works with the Friedman's, and it did also suggest that there is a difference between natural revegetation plant and the planted units compared to the control unit, but no difference between the planted and natural revegetation. And the post hoc test that I found supports that as well. So as you can see, there's really there's almost a significant difference between the planted and the natural revegetation unit, but it's still yet not below that 0.05 value. And then the code for that post hoc test also spits out a nice box plot. So it gives you the ability to look at where those p-values say something is significant. You can look at it visually and see whether it's greater than or less than in its significance. So as you can see, there's the control unit has considerably less native grasses than the natural revegetation or the planted units. So those same tests I ran on the forbs, and once again the parametric ANOVA gave me a p-value that showed significance, and then the Tukey's showed that significance was between the planted and the control unit, but there was no difference between the natural revegetation and the control, or the planted and the natural revegetation. So only one of the comparisons was significant. The non-parametric version also supported that, in that the planted and control units were the only significant difference when we were looking at percent coverage of native forbs. And the post hoc test gave us the p-value, and as you can see, it is indeed significant. And then looking at the box plots for the forbs, you can see that they're at least the median is a little closer between the treatment units, but still yet our test told us that the planted is significantly different than the control. So just a brief discussion here. The results tend to line up with what my hypotheses were, except there was no significant difference between the natural revegetation and the control when we looked at the percentage cover of the forbs. But with continued herbicide applications, as we plan to do in these natural revegetation units, and with time as that succession takes place on these study sites, I believe this will change, and in the end, I believe there will be a significant difference between these two treatment units. So all of that said boils down to is that planting may not be necessary. So this could possibly have effects as far as management long term for land managers. If we can say that our study showed that there was really no difference between the plant community on areas that have been revegetated naturally just by using herbicides compared to planting these expensive seed mixtures, then this has potential to save money and time. So hopefully we can, over the next 2 field seasons, we can gather more data and really drive this point home, hopefully. And if not, that's okay too, but that's what we're wanting to do, is just see if there is differences. One thing that I wanted to mention, that difference in the forbs between the planted and control unit that was significant, I believe that is not an effect of our actual seed mixture that we planted, but rather an effect of an herbicide that was applied during that planting process, which helped control the weed competition. And that same herbicide was not applied on the natural revegetation units, at least not initially at the same time it was applied on the planted units. So I just thought I would throw that out there. I found that kind of interesting, and I believe that's what's going on there. So with that, I'll sum up. And photo credits, all the photos were mine. And then the land cover map was a USGS map, and then the tall fescue distribution map came from West 1998. And there's my literature cited. If anyone is interested, I would greatly appreciate any comments that anyone might have about my proposed methods of analyzing this data. I'm very new to statistics, and or at least on the graduate level, and I would be glad to accept any comments and any help that anyone has to offer. And with that, I will conclude.